Hi, we are going to look in this video at solving non-homogeneous linear ordinary differential equations. And this is actually in section 5.5 of our textbook. The first thing you see here in our outline is a theorem that's actually stated in sections 5.1 and 5.2 of our text, but we didn't need it till now, so I didn't talk about it in class until this point. Alright, so let's look at what this theorem says here. So there's a lot of notation. I want to emphasize a couple of important things here. It says this y sub p is a particular solution to this nth order, right? We've got an nth order derivative here. Linear, you can look at that form. You should recognize that as a typical linear form ordinary differential equation. And if this f of x function is not the zero function, then it's a non-homogeneous differential equation. And so you can see over to the side here, there's an example. And this is one of the examples from our notes, but you'll notice that we have, instead of x and y variables in our example, we have t and y variables here. But you see that we have this function on the right-hand side here that is a function of the independent variable, and that's not a coefficient function for any of the dependent variable terms. So that 3e to the 2t is what makes that differential equation non-homogeneous, and what we are going to be talking about how to solve today. Alright, so our yp is a particular solution to this non-homogeneous differential equation, and yh, so we need to pay attention to those subscripts there, is a general solution. So that will be important, a general solution of the associated homogeneous equation. All right, so we really haven't done that yet here, but the associated homogeneous equation, notice that that is exactly the same as the original non-homogeneous differential equation. It just has that f function replaced by 0. So we're just letting that right-hand side equal 0 for this associated homogeneous equation. Then y equals yh plus yp is a general solution to the equation that we started with. Alright, so essentially this is telling us that we kind of have two main steps in solving these non-homogeneous differential equations. So one is to find the yh. So remembering general solution, so we're going to find a basis for the solution space and then write a generic linear combination of that, which will represent all the possible solutions to that homogeneous differential equation. And then the second main step that we're going to need to do is find that yp, and we're going to add those things together to find our general solution. Alright, so if we look at the example that we have over on the other side here, we can think about, for this particular example, the associated homogeneous differential equation would be y double prime minus 3y prime minus 4y equals 0. And we already know how to solve that. That happens to be a second order linear ordinary differential equation with constant coefficients. So we can write the characteristic polynomial and solve it that way. So that one's pretty easy to find the yh for. Those are basically the only kind we've learned how to solve so far, those constant coefficient linear ordinary differential equations. But we will later learn how to solve some that are not constant coefficient, but that would be how we would find the yh. And then we have to find the yp. Alright, so at least at some level, we already know how to do this, at least differential equations like we are looking at here. We know how to do that. But this yp, this particular solution part, this is what is new that we are going to be talking about today. And then we want to remember that what we're really after is a general solution to the original non-homogeneous differential equation. And so we're going to just add together kind of our two building blocks here to get our overall general solution. Sometimes I see students forget to actually put the pieces together and write down that general solution. Okay, so we're actually going to talk about a couple different methods for finding the yp part. Essentially two methods that are both in the same section of the textbook. So the first method is called this method of undetermined coefficients, and that is probably the easier method in most cases, but it doesn't always work. So we're going to talk about that. We're going to look at several examples of that, but then don't forget that there's also a second method that we will learn in this section. And so the last part of the outline for this section's notes covers that second method. It's called variation of parameters. All right, so let's dig in. And this is basically how do we find the YP. Okay, so let's look at these steps here. All right, step A. Solve the associated homogeneous equation to find YH. All right, so we know how to do that. So I'm going to actually scroll over here and go ahead and do that for this example that we have over here. So then we've got our YH. So we've just taken all linear combinations of those two functions that form that fundamental set of solutions for the differential equation. All right, so I'm going to circle this. This is not my answer, but I'm going to need to use that to put together with my YP to find my answer. So I want to be able to easily find that in my work. So when I come back to it, I can find it. All right, so let's kind of look at the rest here. So that was pretty easy. Finding the YH was pretty easy for this problem. All right, next it says be sure that f of x is of a form for which the method of undetermined coefficients is an appropriate choice of method. So the question is, how do you know when it's an appropriate form? And essentially that is that you can do that next step here. So let's talk about that, and then I'm going to come back up here and write something down. So step C says, based on the form of f of x, make an appropriate guess for yp. The guess should include terms that represent all linearly independent functions in the terms of f of x and all of its derivatives. F of x and all of its derivatives. And that f of x is that right-hand side function in your differential equation. Okay, so if I look at this example over here, this f of x function here, f of t in this case, that's 3e to the 2t. And if I think about that function and all of its derivatives, it shouldn't be too hard for you to realize that all of its derivatives are just scalar multiples of e to the 2t. So I'm going to write these derivatives out for this first one, but generally I wouldn't write out a bunch of derivatives there. I might just think about that function, and all of its derivatives are all scalar multiples of e to the 2t. So the linearly independent functions in f of t and all of its derivatives, they're all basically built out of e to the 2t function. So they're all scalar multiples of e to the 2t. All right, so e to the 2t is kind of that basic building block for that f of t function and all of its derivatives. All right, so this is a perfect kind of problem for this method of undetermined coefficients because that was a very short list of that function and all of its derivatives. They're all basically different versions of the same function. And so that's how you know when this is a good choice of method. This f of t and all of its derivatives, when you think about all of those functions, I'll use x here since it says x in the notes here. F of x and all of its derivatives should form a finite list of functions except for scalars out front. All right, so I need to be able to make a guess that includes terms that represent all linearly independent functions in the terms of f of x and all of its derivatives. All right, so in the example we were looking at there, that f of x and all of its derivatives were scalar multiples of e to the 2x. So I'm going to guess, there was a textbook I taught out of before that called this the method of the lucky guess. It's not really a lucky guess, it's an educated guess. But you're going to guess that that yp function is some constant times e to the 2t. And up above I used c, and here I used a. It doesn't really matter what you call it, but we need to eventually figure out what that constant is. So the next few steps here are going to involve figuring out what that constant is out front. This next part will feel a little bit like what you do with partial fractions, where you have unknown constants, a, b, c, d, whatever, and you have to figure out what they are that make the equation work that you're working with. Okay, so let's look at these next couple steps here. So we've made a guess here. The guess should include terms that represent all linearly independent functions in the terms of f of x and all of its derivatives, so I've made that guess. This next one we actually don't have to worry about in this problem, but I do want to mention it, and we will look at some later examples where we have to deal with that. So it says if there's any duplication in your guess for yp with any of the functions in yh, then you're going to multiply your guess by x to the s. S is this letter our textbook uses here, where s is the smallest whole number power necessary to remove the duplication. So that doesn't happen in this problem, but the reason is I look at this e to the 2t function that I've got here as kind of this basic building block for my guess, and then I look at the functions that are in my yh, e to the 4t and e to the negative t, and those functions are all linearly independent from each other, so I don't have any duplication here. So I don't have to worry about that on this problem. We will look at some later examples where we have some duplication. Be sure you watch those videos because those are a little bit harder. So the guess I'm going to be able to use is just y equals a e to the 2t. Okay, so I'm just going to kind of talk through these next two steps here a little bit, and then we'll go finish up. All right, differentiate your guess for yp as necessary to substitute into the differential equation. So we have a second order differential equation, so we'll need two derivatives there. We're going to substitute in. And then you want to group like terms on each side of the differential equation and set the appropriate coefficients equal to each other to determine the values for the unknown coefficients. This is the part that will feel a little bit like partial fractions, where you determine the values of the a, b, c, whatever coefficients you have that will make the equation work. Okay, so occasionally I have a student who just makes a guess and then they stop there, but that's not really what you need to do. You need to figure out what that coefficient is that makes it work. All right, so let's look at this one here. So I've made my guess, yp equals a e to the 2t. I'm going to need two derivatives since I have a second order differential equation. I don't want to absorb that 2 into the a because I'm going to plug in for the function and the first and second derivative, and they'll all involve some a's there, and that's the same a, so I need to keep track of what these coefficients are. All right, so I've found the appropriate derivatives, and then I'm going to substitute into the differential equation. All right, so for the second derivative, I'll have 4a e to the 2t. And then the next term in the original differential equation says minus 3 times y prime. So that's 2a e to the 2t. And then minus 4y. I'll go ahead and put parentheses there, even though I don't really need them. And that should all equal 3e to the 2t. So I'm substituting that not into the associated homogeneous differential equation, but the original differential equation that we're working with here. All right, and in this problem, it's pretty straightforward because I've got a couple of terms that will cancel, a 4a e to the 2t and a minus 4a e to the 2t. And then that term in the middle simplifies to be minus 6a e to the 2t, and that should be equal to 3e to the 2t. And so if that's true for all values of t, then my coefficients are going to have to be equal to each other. So I'm going to have minus 6a equals 3, so a is equal to negative 1/2. All right, so then that gives me my yp. In this problem, only a was all I had to find. So remember that the general solution is y equals yh plus yp. And that represents all possible solutions to the differential equation that we have. And so those C1 and C2 can take on all different real number values. So I've really got a family of infinitely many functions here that form all solutions to that differential equation. All right, there were a couple other things I want to mention. They don't apply to this problem, but I do want to mention them in the outline here. All right, so write the general solution. I did that. And then the last thing we didn't have in this problem, but you will have in some of your homework, at the end, that's when you want to use initial conditions. So we do have some coefficients C1 and C2 in the general solution. If I had initial conditions, now is when I would want to use them to find my C1 and C2 values. Sometimes I see students try to use those in the YH, and so those would work for the homogeneous equation, but they're not going to work for the original non-homogeneous differential equation that you might be working with. The other thing I want to mention here, and we'll look at a later example about this, if the f of x, that function on the right-hand side, is a sum of functions of different types, you can separate it into separate functions, sub-functions, and proceed as above for each sub-function. And then your yp is kind of based on these different parts. So for example, if your f of x on the right-hand side of the differential equation involved, say, a quadratic polynomial and an exponential function, those are really two different function types, a polynomial and an exponential function. Those are two different function types, and so you would make part of your guess based on x squared and all of its derivatives. Those are all just different polynomials of lower and lower degree. And then another part of your guess would be based on e to the 2x and all of its derivatives. So kind of chunking the functions into different types, polynomials, exponential functions, trig functions, etc. All right, one last thing I want to mention about this before I stop this video here is that you might notice on this one it was very straightforward because that right-hand side of the differential equation was this exponential function. And you know that when you take the derivative of an exponential function, you get back a scalar multiple of the same exponential function. And then I mentioned also that polynomials also work really well with this. So when the right-hand side of the differential equation is a polynomial, when you differentiate polynomials, you just get more polynomials of smaller and smaller degree. So an exponential function, a polynomial, and then certain trig functions work really nicely too. If I think about a sine function and I take derivatives of sine functions, I get cosine functions, and then a derivative of that gives me a sine function. And so those functions just give back derivatives of each other. So sine and cosine function are other nice functions for which this method works pretty well, or combinations of those. So those are the kinds of functions that often are on this right-hand side of the differential equation if you're going to be using this method of undetermined coefficients, because they give back themselves or different versions of themselves when you take repeated derivatives of them. So you might think about that kind of as you're working through the homework and notice the kinds of functions that work well in this method. And then when you do homework from another section later, you want to pay attention to those kinds of functions and why a different method is necessary for those. So just kind of keep that in the back of your mind as you look through some more examples. All right, so watch some more videos for some more examples.